Okay, so we can start today. I am Giacomo Gradenigo. I am one of the organizers of the present series. And today we will have as a speaker, and we are very, very honored to have him, Édouard Brézin, who will introduce us our work on planar diagrams. And I want to say just a couple of words on Édouard. Édouard, among the many awards, he received the Langevin Prize in 1974 and the Dirac Medal in 2011. And what I would like to say is that he is one of the best representatives of a golden period of theoretical physics, where there was a very strong cross-fertilization between statistical mechanics and quantum field theory. And as you can see, he has been the editor of books which are precisely related to this target, because you see the large N expansion in quantum field theory and statistical physics, and you can read in the title from spin system to two-dimensional quantum gravity. So you really have the taste of an overall background that are relating all these important topics in science. And also you can see the title of the Lesouche proceedings, which is Fields, Strings, and Critical Phenomena. And in fact, Édouard is one of the biggest experts of all these fields. So now I'm happy to leave the stage to Édouard in presentation. So here we go. Thanks a lot, Édouard.
Thank you. Thank you for the kind introduction. It's a pleasure to be back here because I've been several times in this room, and in particular on behalf of Giorgio. Being here and having to speak of a 44-year-old paper, that reminds me of a story you probably all know about our late friend Miguel Virasoro. As you know, Miguel in his early days had worked on high-energy physics and particle physics, and then he moved to disordered system. And he gave a talk later in his career, and at the end of the talk, someone asked him, "Are you the son of the Virasoro?" So he was very happy to be taken as the son of the Virasoro. So this is not a paper by the father of Giorgio, but by Giorgio himself. So, there are more papers, there are more authors I have to show you. It's, of course, a subjective account of this work. I will use a mixture probably of slides and blackboard. I like the blackboard better, but this is an outline. And the warning is that it's rather technical. I'm sorry, because if I don't use anything, it's not working. I can use that. Okay. We'll get the next one. Okay. So it's based on planar diagram, this paper by 4 authors. Unfortunately, Claudette Sixon is not there anymore. And this paper of 1978 was, I would say, not very considered for a long time. It's only at least 10 years later that suddenly it became very successful and quoted all over. And I will give you an idea of why this paper became more important, or at least more quoted than it used to be initially. So I will, Spenta Wadia, who was one of the authors of the book you showed on large N, gave a talk after Giorgio got his Nobel Prize in Bangalore, where he has founded an Institute of Theoretical Physics. And this is a copy of his first slide. And his slide was celebrating Giorgio, planar diagram, and large N limit. So in his view, he's not a statistical mechanician. That was an important contribution of Giorgio. When he said this is foundational, it goes too far, of course, but it's too loud, or, okay. So let me start with large N, and I will first go to the blackboard. The large N history starts with a trivial large N, which is vector large N. And this was invented by, in fact, accidentally, was invented by Gene Stanley, 1968, who took a model of a generalization of the Ising model, in which the Hamiltonian is minus J sum on nearest neighbor of SI dot Sj, in which the SIs are classical vectors of unit lengths. And he says that if this is S1 square plus Sn square for the site I, if n goes to infinity, this model is trivial. And indeed, it's very simple. The idea is that you simply add a Lagrange multiplier for the constraint. And then you can integrate each component. If you integrate on every component, this will generate something like a determinant of Jij plus alpha I to the power n, because you can integrate every component of the spin independently. And therefore, since you have a determinant to the power n, when n goes to infinity, it goes to saddle point. So it's simple. It's simple, useful, a little limited, and we'll see in a second what are the consequences of this trivial model. I think it's Ken Wilson, without publishing, which happens from time to time. In 1972, Wilson asked what happened in field theory for large N. And Wilson, as you know, had just considered at the time, he had just invented the renormalization group for critical phenomena. And the model was based on fields in which you had gradient of the field. Let's take continuum limit, m square phi square plus g phi square square. And Wilson asked, is there anything simple when phi is an n component vector, and if n goes to infinity? What happens? And he pointed out immediately, I think he put an n here so that the large N limit is well defined. He pointed out immediately that this model was simple in the large N limit for the following reason, which is interesting to contemplate, because we'll see later that it's not always as simple. So he said this model has an interaction. The interaction is G over N, phi I, phi J, which you can represent like that, I, J. That's the interaction. Then if you look for fluctuation, the first one you will get is something like that. And this one has, by construction, 1 over n. So this one has 1 over n, 1 over n. And this has an extra factor of n. And therefore, these two are same order of magnitude. This is n to 1 over n. Then he said, if you took 2 bubbles, you can count in your head, and you will see that this is also 1 over n. However, he noticed immediately, if you take a diagram which is slightly more complicated, something like that, sorry. This will have 1 over n 3 times, but only n once because of this closed loop, and therefore this is 1 over n squared. And therefore, said Wilson, we have to take bubble diagrams, only this bubble, this string of bubbles, and summing the string of bubble is elementary because it's a geometric series, and you can get easily to the solutions. And the solutions are both interesting and deceptive. So this is Wilson. These are the diagram. Again, I've repeated what I just showed. And if I go one further, here are the consequences. It was an interesting confirmation of earlier work by Wilson. The first lines are the large n results. It confirmed that for d greater than 4, the critical exponent, here the magnetization, the magnetic susceptibility exponent was trivial, and below 4 dimensions, it was not trivial. And it agreed with the earlier Wilson-Fisher paper of the epsilon expansion. If you take the large n of the epsilon expansion, you can see in your head that if you expand the second result for n large and the first one for epsilon small, you get the same thing. So it was confirming his earlier work. And in practice, it was not very useful. For instance, more articles were devoted. This one, I think I've quoted here, result by Vassiliev of the expansion in powers of 1 over n. And you can calculate a few terms. It's not so easy. And the result in practice, if you want to apply that to the Ising model, n equal 1, or even n equal 3, it's not very nice. Doesn't converge well, but at least intellectually, it was an interesting model. So immediately after that, the question came naturally, what about cases like Young-Mills, in which the field could be a matrix? So immediately after, many people look at what happened if you take L equal trace of F squared, in which F is a matrix in the Lie algebra of an adjoint representation of SU3. So F would be a traceless 8 by 8 matrices. 3 by 3 matrices, there are 8 independent matrices. So the immediate question at the time, we are back to 1973. The immediate question was, well, SU3 is very difficult. As you know, it's still one of the Clay Foundation Millennium Prizes. In 2000, the Clay Foundation posted 7 mathematical problems to be solved for $1 million if someone could solve. and there are still 6 unsolved. The only one which was Perelman's Poincaré's conjecture, but he refused the prize. And the only one which concerned physics was this one. And the question was, can you prove that in this model there is a mass gap? So if you could prove that this model has a mass gap, in other words, if color is confined, then you will get the Clay Foundation Millennium Prize. Of course, this is still an open problem for mathematical physics. And the immediate question was, what happened if you try the simple generalization SUN? What happened for SUN if n is large? And based on the previous examples, many people, including myself, tried and came to the conclusion that nothing simple happened. So instead of this model, which has a lot of indices, we took it instead a matrix, degrees of freedom. So phi of x is an n by n Hermitian matrix. And the Lagrangian would be gradient phi square trace plus some v of phi. For instance, v of phi is phi square plus phi fourths. And let me put an n here. So what happens? Well, guided by the previous example, we started looking at Feynman diagrams. And so now we need, since phi is phi I j, we need double line to represent the internal index. So this is the phi to the 4 interaction. Here I've taken phi to the 4th. And if you look at that, so this has an n by construction. If I look at the bubble, you see that there are n at each vertices, but each propagator by my normalization has 1 over n. And therefore, this, I'm sorry, I'm doing here something wrong. There is 1 over n each propagator. So this is n to the 0. What did I do wrong here? Let's go back to my slides. Yeah, there are 2 n's at the vertices, 1 over n for the propagator, and 1 closed loop inside. I'm sorry, I forgot this closed loop inside. So this whole factor is n to the 1, like the previous one. So if you look at the double bubble, it's also n to the 1. So you would say, well, it's going to be simple, summing bubbles. Until, disaster, you go to the diagram, which is to the right bottom over there, which in the previous example was down, was subleading. And here, it's also n to the 1. If you count, there are 3 vertices with factor of n. There are 4 propagators with propagator 1 over n, and there are 2 closed loop of internal index. So total is n. So nothing simple there. So I remember in 1973 meeting Ken Wilson at a conference and telling Ken, we have tried large n for young meals, and Ken's answer immediately was, well, it doesn't work. In other words, he had tried, like ourselves, this, and from this seems that nothing simple happened for gauge theory in large N limit until the year which followed, in which 't Hooft realized the following. In fact, if you compute log z and expanding in power of 1 over n squared, in fact, the coefficient of 1 over n to the 2h is the sum of contributions of diagrams which can be drawn without crossing on a surface with h handles, h being 0 for the plane or the sphere, compactified plane, or 1 for the 1 torus, etc. So the leading contribution, said 't Hooft, for larger n is not everything, it's simply the planar diagram. 't Hooft's argument was not too difficult. I will give you first an example. So on the top diagrams, they are the planar one, the only one by laziness that we are all considered, which are all of the same order of magnitude. But indeed, as 't Hooft said, if you look at the last one, it has 1 over n instead of factor n, and it's clear that the next one can be drawn without crossing, not on a plane, but on a torus. So it's a topological expansion, and the argument of counting powers of n of 't Hooft was very simple. He said, you put n to the power on every vertex, I'm sorry, you put 1 over n for each propagator, you put an n for any closed loop of internal index, and if you use the earlier Poincaré relation, you get that the factor of n is 2 minus 2h. In other words, if you divide by log z by 1 over n squared, you have a series expansion in powers of 1 over n squared to the power h. So that was a brilliant and very influential remark of 't Hooft. And after that, we come to 1978. Giorgio was visiting Paris and Saclay, and we got together with Jean-Bernard Joubert and Claude Itzigson and Giorgio, and we were dreaming of summing those planar diagrams. Okay, it's not a simple series of bubbles, but can one do something? Can we really compute this sum of planar diagrams? And we didn't come with any brilliant idea to sum them in 4 dimensions, which was, of course, the ultimate goal. And not succeeding very much, we ended up in a retreat asking us simply, how many diagrams of order k are planar? It's easy to see that at order k, if you don't have any topological restriction, you have about k factorial diagrams multiplied by some number to the power k. But how many diagrams are planar at order k? So that was the beginning of this collaboration. And it's clear that if you write an integral simply over matrices, you get into a counting problem. In other words, if I write the integral over m, which are n by n emission of exponential trace of m squared plus v of m, say trace of n fourth, you can expand in power of g, apply Wick theorem, draw Feynman diagrams, but every Feynman diagram will be trivial. There are no momentum integration. There is nothing, just counting how many diagrams. So if we simply expand in power of g, the coefficient of g to the k is simply the number of Feynman diagrams. However, if we make a double expansion, 1 over g to the k, 1 over n to the 2h, the coefficient c h of k, this coefficient is simply the number of diagrams which you can draw on a surface of genus H with k vertices. So if I write 1 over n squared log z, and if I compute ch of k, we are done. Well, when you have large matrices, it's not so easy to calculate this integral over the matrix. And fortunately, there are lots of techniques which have been used, but in that particular case, we invented with our friend our technique by saying, well, the measure is unitary invariant. Therefore, if I write M equal U diagonal matrix times U dagger, lambda being a diagonal matrix, then nothing in the integral depends on U, and therefore we can integrate over U, and we have, instead of an integral with n square elements, we have an integral over n elements. However, there is a Jacobian dm is the Haar measure on the unitary group multiplied by the integral, the d lambda I times the Jacobian, and this Jacobian is very simple. It's product on I smaller than j, lambda I minus lambda j squared. Therefore, you can integrate completely over the unitary group, and you get instead that this integral is integral d lambda I times exponential minus n sum over lambda I squared plus g lambda I force plus sum I smaller than j log of lambda I minus lambda j coming from the Jacobian. Well, in order to make this a little more transparent, I have written this again in the last line of the slides. This is the integral, except that I've introduced rho of x, which is the density of eigenvalues. And you see that if you look, maybe this has a pointer. Yes. So this term is the lambda I plus lambda force times the density. And this term, rho of x for y, is just the Jacobian. And you see on this, given this n square, and the fact that there are only n integrations, which is very small compared to n squared, the saddle point is exact. And therefore, the large n limit is classical, is just the minimum of this effective action over lambda. In other words, E0 of G, the leading term of this for large n, is the minimum with respect to rho of x of this action, which is quadratic in rho. So it's simple to take derivative with respect to rho. And here I've taken one more derivative with respect to x. And the result is an integral equation on the density of eigenvalues. And this integral equation is well known in mathematics. It's called Wiener-Hopf. And the solution is completely explicit. And let me look at the solution here. So no, I went too far. Here. So the solution is that rho of x look very much like Wigner's semicircle. If A was equal to 1, when G equals 0, this parameter A is just 1. So if G was 0, A would be 1, rho of x would be Wigner's semicircle for large matrices, Gaussian matrices. For these non-Gaussian matrices, we get a slightly shifted, slightly modified semicircle, but it's completely explicit. And as you see, the ground energy is explicitly given as a function of G. So we have succeeded if E0 of G is here. The E0 of G in the slide above is simply C0 of integral C0 of K, G to the K. So this gives the solution. And it's interesting to look at the properties of this solution. The first one is that it's analytic in G for G positive, but it can even be continued to negative G. And this is something which is not obvious a priori, because as you see for negative G, the integral doesn't make sense. The integral with a negative trace M force is not defined. However, the 1/n expansion is well defined. Term by term, the 1/n, in fact, this is the leading term, but you can show that term by term, the 1/n contribution are analytic in G in a cut plane with a singularity at G equal here -1/48. So that was not obvious. The second point that one got from this is that the number, I keep changing notation, which are called C0 of K on this blackboard, are AK in the upper blackboard up to a sign. And it's easy from the explicit expression to count how AK behaves for large K. There are explicit formulae, so it's a simple exercise. And what you find is that AK behaves as some number to the power K. And you will remember that if we didn't have the topological constraint, CK, CH of K would behave, I mean, the coefficient of G to the K would behave as K factorial. So planar diagrams are rare, 48 to the K compared to K factorials, but still it's a lot. And the planar limits, they are all analytic, as I said, for G greater than -1/48. And remember this -1/48 because later it has been used to define what's called the double scaling limit. So the first, I mean, this paper, which is not enumerations of graphs, was in fact the first problem, to my knowledge, in which familiar algebraic method, familiar to all of us, were used into a problem of enumeration. And one of the descendants of this old work is still alive. It's still among mathematicians and physicists who are using such algebraic technique in various problem of enumeration. For instance, if you ask how many irreducible diagrams there are, we are all familiar with one irreducible. We are all familiar with that from field series. Therefore, this has been used a lot by mathematicians and combinatorics. However, before, in this old paper, we also succeeded to go to one dimension. In one dimension, we are dealing with something, it's a linear chain, if you want, of matrices. They are coupled by nearest neighbors, which I've represented here by trace of m dot square. So in one dimension, in the old paper, with the 4 authors, we succeeded to solve this problem, or at least the ground state for such problem. And the result was rather surprising. Let me show what we did at the time. So this path integral, as we all know, this is quantum mechanics, can be replaced by the Schrödinger equation. The Schrödinger equation would contain a Laplacian with respect to the n² degrees of freedom of the matrices, plus an interaction term, which is the trace of V of m on the wave function is E psi of m. Now, the ground state, if it was quantum mechanics, we would say it's an S state, rotational invariant. Here it's UN invariant. And therefore, the ground state, which by the way is symmetric under permutation of the lambda, it's an easy exercise to calculate the Schrödinger if we take into account the fact that the wave function is only a function of the eigenvalues of the matrices, psi of the lambda. And a simple exercise shows that here is the expression of the Laplacian with respect to the lambdas. Of course, in the full Laplacian, there are Lij squared divided by lambda minus lambda j squared, but for the ground state, which is an UN invariant, this is enough. So the form of the Laplacian immediately leads to consider the wave function multiplied by this antisymmetric function, which is the product of lambda I minus lambda j, which is called a Vandermonde determinant, whatever is its name. And if you do that, phi is the new wave function. Immediately, you see that the wave function satisfies Schrödinger equation, which is minus d by d lambda squared plus v of lambda, sum over I equal E psi. But this is remarkable because these are independent lambda I. The wave function is decoupled, and any product of eigenfunctions of a one-body Hamiltonian is a wave function for the n-body. But given that psi was symmetric, phi is anti-symmetric. And therefore, we are dealing, in fact, with a problem of n fermion in the potential well V, and the ground state is filling up in the potential well until the Fermi energy. We have V of lambda. If I take lambda force, we have our V, which is here, and we have to sum until the Fermi energy, n level. And that's the answer. That's the ground state energy. Very surprising. Or at least we were surprised. And since most level, n is very large, since most levels are highly excited, you can replace the true quantization, the true Schrödinger equation, by a semi-classical approximation, because it's high quantum levels. And thus, we found that the final formula, they are below, a classical expression for the eigenstate, the energy of one state in the world, times a theta function for the Fermi energy, and the number of wells, the number of level determines the Fermi energy. So that gave the answer for one dimension. And again, much later, this was the basis of many papers on what was called central C=1 matrix models. There were many articles, in particular with Giorgio alone, or with Giorgio and collaborators. You have all seen the chart of Giorgio's collaborator. It's a wonderful chart. I was happy to see my name somewhere there. And okay, so that's the end of the old period. I've shown what we knew in 1978. And if I really look backward, it was, we published what we had been able to do, but it was really an account of a failed attempt. We really wanted to go to 4 dimensions, or at least more than one, and we never succeeded. However, this paper came back later in what is called 2D quantum gravity and matrix model. So this is much later, and a lot of things had happened later. First of all, 2D gravity. 2D gravity, why should one be interested in 2D gravity? So the Einstein's action would be the integral on, in that case, 2 dimensions, square root of the determinant of the matrix times there's something like the gravitational constant and pi's floating around. And here is Einstein's action for 2D gravity. But this is completely trivial because it's known from a theorem of Gauss and Bonnet that this number is a pure topological number. It's probably some number, I forgot how many. What's the number? There are pi's here. But times 1 minus the, I hope it's 1. It's 1 minus the genus of the manifold. As a consequence, since this is topological, if you vary this, the variation is 0. In other words, any matrix is a classical solution. So classically, the model doesn't make sense, or it's not interesting at all. However, if you take quantum mechanics, in which you want to sum over all possible manifold of the exponential, the fact that h can vary makes the problem slightly more interesting. It's also more interesting because Polyakov had formulated a theory of a relativistic bosonic string which he mapped into 2D quantum gravity. It was what Polyakov had done. He returned to the old Nambu-Goto action, and which was quadratic. He linearized it and showed that, in fact, 2D quantum gravity was the same as the string equation that Nambu had introduced. Now, in 1985, so that's a fact. In 1985, several authors, David, Kazakov, Fröhlich and co-workers, I think Ambier and Durus, define a model of 2D gravity, which normally requires an integration over all Riemann surfaces by a discretized sum over random triangulation. Let me show that. This is I took in the advertisement of some paper pen factory. So this is a triangulation of a surface. And you want to sum of all possible triangulation. Now, if I return to the action, I can add here some cosmological constant. And eventually some coupling of matter to gravity. Now, what happens if you replace the random surface by a sum of a discretized sum over triangles? By the way, if you prefer squares, they are allowed as well. Just small plaquette representing this. Then if you do that, what happened to the discretized action? Well, we know that the first term is proportional to h, the genus, up to a constant, proportional to the genus of the surface defined by the triangulation. The second term is, of course, the area. And for the moment, let's take this pure gravity without matter. So the partition function, once you have discretized, is sum over lambda and mu of sum over, over h and here an area of exponential minus mu h minus lambda a. That's the discretized sum, which replaces multiplied by some coefficient here. This coefficient being the number of surfaces of genus H and area A. That's the partition function. So the author, Kazakov, David et al., realized that the triangulations are dual to Feynman diagrams. So I'll write the dual diagram. So the dotted line diagram I've not finished. The dotted line diagram can be considered as a Feynman diagram of some sort, and in which the vertices are triangle or in fact squares. In the case that I've drawn here, the field theory which would give the dotted diagram is a mixture of phi cube and phi fourths. And therefore they say, let's take this as definition of 2D quantum gravity discretized. I've reproduced over there. Of course, the field theory, which have double lines, here it's the opposite, I'm sorry. The initial triangulation have taken opposite convention. I hope this doesn't trouble you. The dotted line are the initial triangulation. The double line are the Feynman diagram, which are dual to the dotted line. And I've put double lines because I'm interested in a given genus. And we know from Toph's works that if we want to fix the genus, we should have matrices as degrees of freedom. With the same story. And I've reproduced here if I consider the matrix integral here with m cubed instead of m4, doesn't matter, then the logarithm of the partition function may be expanded in a double sum in 1 over n squared, the number of vertices, which will mean the number of faces of the triangulation, multiplied by a counting factor, which depends on the genus and how many faces I have. So in some sense, in this formulation, 1 over n squared is like the chemical potential for the genus of the surface, and G or log G is the chemical potential for the area of the surface. Therefore, we have to calculate these numbers and go to the continuum limit, because of course we are not interested in a discretized diagram, but try to go to the continuum limit. And that was not so easy. And a lot of people worked. And you remember I said earlier that for fixed genus, the sum of diagrams for a given Euler character diverges as some critical value GC. You remember maybe my -1 over 48 of the first slide. Therefore, the sum of diagrams drawn on the surface with H handles are all singular at the same GC. And therefore, at the singularity, the number of diagrams will diverge, and we will get a continuum surface. So we have to go to this continuum surface. In the continuum limit, I have to speed up. In the continuum limit, the scaling limit, there were earlier results by Polyakov, Knizhnik, Zamolodchikov on the basis of Liouville theory, which gave the critical exponent for the behavior of the continuum surface with area A and handle H. And here are the Polyakov et al. Generalized to arbitrary H result. For pure gravity, if I don't put any matter, the central charge of the conformal is 0, and we are just dealing with -1, m is 2, and we are just dealing with gamma is -0.5. Then, since the partition function is the sum, the last line, of Z of H and A times X, the chemical potential for the number of holes on the surface, and since we take the first line for the behavior V of H and A, we expect a scaling limit, which for some reason was called the double scaling limit. This was all done in 1980 something by Gross-Migdal, Douglas Schenker, and Kazakov and me at the École Normale. We expect a scaling variable, which they call the double scaling limit, in which we approach GC when we get a power of n, because we need all genera, not simply planar in this game, and the power is -4/5. And indeed, what we find is, first of all, we recover the exponent of Knizhnik, Polyakov, Zamolodchikov, but in addition, we got an explicit expression for the partition function, or rather here it's second derivative with respect to the coupling to the cosmological constant lambda, with a function f of x, and f of x satisfy the string equation which is there, which is called PinV1 problem. So that was the first complete solution of a string model, analytic. There was nothing before. And this is probably why at that time, matrix model had a considerable number of quotation. And this is why there was a revival of our old paper with Giorgio. I think I will stop there. The derivation, I've not given it here. It would require another full lecture. It's not difficult, but it's a full lecture. And the conclusion, our attempt to solve the large N limit for Young-Mills failed. However, the solution for the counting of planar diagram led to the matrix model of 2D quantum gravity, bosonic string theory, and opened a new path in combinatorics. So I'll stop there, tell you how I'm happy to celebrate with you, Giorgio, and how it has been for me important to know him for exactly 50 years since we first met in 1972. This had a considerable influence on many people at many stages of my work. And as I know, we can expect a lot more from Giorgio in many other directions as well. Thank you.
So thank you very much, Édouard, for the very clear and fascinating talk. And if someone has questions, remarks, perhaps maybe Giorgio wants to make some comments on this, say some words. I don't know.
Yes.
I think that the whole reconstruction is very clear, and it's quite amazing what you say, that we were looking for something that we could not find, and we found, and we help other people for finding something else. The other thing that struck me that is quite magic, that if you look to the one-dimensional case, which can be solved, as you said, with fermions and all stuff. If you look to the path integral formulation, the path integral formulation seems very, very difficult at this stage. I mean,
no, there are solutions for chain of matrices.
Yes,
trace of mi plus 1. Yes.
Yes, you can do, but it's much more.
Yeah. Yes.
You need a lot of work because you have to
Yes,
do
of
the,
course. Yes. Yes.
to the integral.
You're right. This is infinitely simpler. Yes.
Yes, and this is the fact that the spectrum, the ground state is much, and also maybe the first excited state are much simpler than the computing the old dynamics. And I think that since we went on for some reasons, try to see if there is some trick in 2 dimensions that could be helpful, but we never found.
There is a question there. Yes. I cannot hear you. Please wait.
Failure of solving large N Young-Mills, pure Young-Mills, is related to the fact that eventually the perturbative series in the 12th coupling has 0 radius of convergence. That's it.
Yeah.
But for higher supersymmetric theories like N equal 4 or conformal theories, that becomes finite.
Yes.
Or infinite, actually.
Absolutely. And N equal 4 tends to be particularly beautiful and simple, but yeah, that reminds me that after this rage on matrix models, they were all bosonic. So there were an enormous number of attempts to generalize what I showed here with fermionic degrees of freedom for the full string theory, and nothing, to my knowledge, nothing very successful in that direction, except what you say, N equal 4 supersymmetric Young-Mills. Yes.
Okay, thanks.
Okay, I have one last question.
Please.
So I have a curiosity. So I have a tiny impression, I'm not sure, but how much is those results, those from you, George or Toft, related to a nowadays very fashionable idea and topic that is the gauge and gravity duality? Because it seems something that is emerging to some extent, the duality between the triangulation and the large N gauge theories.
There were a number of people quoted. Kazakov was, at the time in Moscow, was the first to think of this triangular approach. François David at Saclay as well was not very far from us at the time. We were all at Saclay. Giorgio was visiting Saclay. So these people contributed a lot to this discretized gravity. Nowadays, matrix models have been done. They are part of the books, and I don't see much interest left, except that this is part of the solutions. There had been a number of speculation, in particular by Steve Schenker, on this Painlevé equation and the behavior of strong coupling for gauge theory. He pointed out, by looking at the perturbation expansion of the Painlevé equation, that the behavior for strong coupling was not what one would expect from Toft's coupling. It was much milder. And he speculated whether this would be a generic property of string theories. I don't know, I'm not enough of a string theory to comment, but I know that Steve started from there.
Thank you very much again. And now we have the coffee break right outside here.